Welcome to the module on feature engineering. It is one of the most fascinating modules and aspects of the machine learning paradigm. But before we dive into it and move ahead, let's quickly take a look at what we've covered so far. We used some data to build a machine learning model, where the model is basically a function that tries to learn the relationship between the dependent variable and independent variables. For instance, we covered the following basic algorithms like KNN, linear regression, logistic regression, and decision tree. And if you recall, linear regression is a function y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on, where betas here are essentially the coefficients of variable. Similarly, a decision tree is a combination of multiple if-else statements where we've tried to find pure nodes. Here you might have noticed that I'm not talking about any coefficients because decision tree is a non-parametric algorithm, whereas linear regression is parametric. Note that all the methods we've looked at so far were around optimizing the ML algorithms of finding the optimum model. But we have not majorly worked on the data that we've given to the model. We've just used the existing data and just trained the model on that. We can add more data to the model so that it is able to make better predictions. We can do this broadly in two ways. First, we can add new features or more information to the existing data. For example, if you're trying to predict the daily sales of a product, let's say a cold drink, in a college campus or our office complex. We've been given data for past sales, and using that, we need to estimate the sales for the next 10 days. In this case, introducing a feature like the list of holidays for the next 10 days might help to estimate the sales more correctly. Or how about having a variable like the daily average temperature? Because the sales of a cold drink might vary from winters to summers, etc. It will add more value to our model and will help us in estimating the sales effectively. Here you can see that the addition of these two variables is actually helping us to estimate the sales for the next 10 days. Another way to improve our model's performance is by using the existing data more effectively. Here I'm saying that we can generate more information or signal using the existing features to predict the relationship between independent variables and the dependent variable. Suppose we want to predict whether a customer will be able to pay a loan or not. And we have the details of the customer like the birth year, gender, salary, income, etc. So let's take application date and birth year. These two features can help us generate the age of the customer. This new variable age might impact the performance of the model and we'll be able to estimate the default ratio of customer, right? We can also use the income variable to generate a brand new variable. Currently, income is a continuous variable and we can divide the income into categories, or you can say different bands. For example, low income band, high income, average, and so on. So in this case, we've seen that we can use existing variables to generate new variables like age and income band. This technique of generating new features using existing features is called feature engineering. Let's now put a formal definition to feature engineering. Feature engineering is the science of extracting more information from existing data. We're not adding any new data here, but we're actually making the data we already have more useful with respect to the problem at hand. I've said that with respect to problem at hand, so having a fair knowledge of the domain will always help us to build better features. So I'll recommend understanding the problem statement and the domain well enough, as this will help us to build better and relevant features. In this module, we will look at various feature engineering methods for different types of data sets like date, time, continuous, categorical, text, and others. Here's a small but a very interesting exercise for you. On this slide, we have a subset of the two datasets that we've been using so far: Titanic's survival prediction and Big Mart sales. Now, I want you to take a while and think about what new features you can create from the given set of features for respective problem statements. In the next section, we've shared the problem statement and data dictionary again for both these problems. So please go through it and share the list of features on the discussion portal. It's a very interesting exercise and will help you understand what feature engineering is and how it works. I hope you have a good understanding of the term feature engineering at this point. Now, before we look at the different techniques we can use for feature engineering, let's quickly look at some basic features we can create with the examples we saw before. Here is the Big Mart sales dataset. You can see that we have a feature item identifier. It's the first column here. It has a large number of unique categories if you look at the original dataset. This dataset is a few sample records. But even here you can see that all the categories or all the rows are unique. But if we explore the entire dataset, the first two characters in all these categories seem to have three unique categories. It's either FD, DR, FD again, NC, and after this it's all FD. Now look at the item type against them. NC is against household, DR is against soft drinks, and FD seems to be against food items like dairy, meat, snack foods, frozen foods, etc. So we can conclude that FD, DR, and NC represent food, drink, and non-consumable respectively. Using this information, we can have a new column having values like FD, DR, and NC only, and this might help us to build better models. Let's look at another dataset. Let me pull up the Titanic one. This dataset also has a lot of variables. Again, as I mentioned before, you should read the problem statement and the data dictionary well before starting the model building process. This will help you to think of new features you can generate. So if you've gone through the feature description of this Titanic dataset, you would know that the two variables SIB, SP, and PARCH represent the count of siblings or spouse and parents or child on board. Using this information, we can generate the total number of family members on board. We can add these two values, SIB, SP plus PARCH plus 1, where 1 is for that observation or person. There's another feature I want to discuss, the name. It's a text field. If you look closely at the name column, you'll see a title with each name like Mr., Mrs., Miss, there's a master as well. So these titles can be useful features in making predictions because these titles in a way represent the age bracket of passengers. This might help us to impute missing values in the age column as well. Similarly, we can create many more features using the given data. Now let's look at what we'll be covering in this module. We've seen a few examples of the problem statements in the dataset like the Titanic and the Big Mart sales. Here we had some numerical features, categorical features, and some text or string based features as well. These are the most common variable types we usually find ourselves working with. Another type of feature that we might encounter is the date time column. We'll learn how to deal with all these features in this module. Or in other words, how can we generate more signal from a given data set? For now, we'll turn our focus to numerical and categorical variables. In this video, we'll discuss about the different methods of feature engineering. We can broadly divide feature engineering into two categories, feature preprocessing and feature generation. Let me briefly define these two subcategories. Feature processing refers to changing, updating, or transforming the existing features. In this case, we're not creating any new features, but making the same features more informative. We'll talk about different feature preprocessing methods in the later part of this video. The other category is feature generation. This is where we generate new features from the existing features. But then how is feature preprocessing different from feature generation? Well, feature generation refers to creating new features from the existing data and not simply transforming the values of existing features. For example, in the Titanic dataset that we saw, we've created family size and extracted title from the name. These are examples of feature generation. Let's look at each of these categories in more detail specific to numerical and categorical variables. Let's start with feature preprocessing. There are various methods to perform feature preprocessing and we'll look at them one by one. The first method we look at is called feature transformation. Feature transformation, as the name suggests, is a method used to transform the features using mathematical operations. For example, for a given feature value, you can take the log of the value, square it, or take a square root, take reciprocal, and so on. But I'm sure you're wondering, why is this important? And how can we decide when to use which technique? Well, it varies from case to case. For example, look at this plot. It shows a relationship between a target variable and a feature. This shows that the relationship is non-linear. And we know that for some models like linear regression, it's good to have a linear relationship between the dependent and the independent variables. So in this case, we should transform a variable in a way such that the relationship between the target variable and the feature becomes linear. So this method is very model specific. Let's look at another case where feature transformation will help us to model better. Take this plot for instance. This represents a right skewed or positively skewed distribution. This could be due to the presence of some outliers in the data. Having a normal distribution is preferred over skewed distribution because it makes things easier. It makes it easier to model the relationships. Also, some modeling techniques perform well when we have a normal distribution of variables. So, whenever we have a skewed distribution, we can use transformations which reduce the skewness. Now note that for right skewed or positively skewed distribution, we take the square or cube root or log of variable, and you can call that the nth root as well. And for left skewed or negative skewed, we take square, cube or exponential of variables. This is called feature transformation. Now there's one more thing you should note. If we are taking a log of the variable that has a negative value or a value of 0, it might show an error. Can you guess why? It's because the log of 0 is not defined. So instead, you can use a simple trick and take log of x plus c, where c is a constant. The objective is that the input of the log must be greater than 0. Right? Now let's go ahead and look at an implementation of feature transformation in Python. In this notebook, we'll be implementing feature transformation on the Big Mart sales data. So let's start with importing the libraries and of course loading the dataset. So let's go ahead and do that. We've rigorously worked with this dataset in the last modules, and I'm sure you'll be familiar with all the features by now. So here are all the columns in the dataset. The continuous variables among these are the item weight, item visibility, and item MRP. I'm going to go up and I'm going to take up the item visibility variable here. You can try the same exercise with other variables. So let's go ahead and look at the distribution of the item visibility feature. So here we go. Here's the distribution plot or the histogram plot for the feature. As you can see, this is a right skewed distribution. Let's take a square root of this and check the distribution again. So we'll create another variable, item visibility square root, that will store the square root value of this variable. Here I'm using the np.sqrt function to calculate the square root value. So I'm going to go ahead and implement that and look at the distribution again. This distribution looks more symmetric. We can also see that there are a large number of values which have visibility 0 here. So we'll need to deal with them separately. Now, as we've discussed previously, we can either take the root or the log in case of a right skew distribution. So let's go ahead and use the log function now. Here's another variable we're creating called item visibility log that will store the log values for the item visibility feature. Now when I run this, I get a warning. Can you guess why that is? Here's the warning that we're getting. Well, look at the variable distribution. So let me go ahead and run this. As you can see, we have a minimum value of 0, at least one value. I'm sure there could be more. But the log of 0 is not defined. That is why we're getting an error. One way to deal with this is that we can simply add a constant to every value in the variable. Here I am going to go ahead and add 0.1. And when we see the distribution again, look at this plot. We have mostly negative values. And the distribution is not exactly perfectly normal. This is because the values in the column are less than 1. Let's increase the scale of the values. And keep in mind that increasing the scale will not affect the distribution at all. Here I've multiplied all the values with 100. So let's go ahead and run this code. So the new range of values have changed from 0 to 0.3 to 0 to 30. I'm going to go ahead and use the log transformation again and just plot it out. This plot is a normal distribution and the values, as you can see here, are also positive. Now let's move to another method of feature preprocessing, feature scaling. Take a look at this dataset. It is related to loan applications. Here we have variables like loan amount, EMI, and the income, and these are all in different units if you'll notice. So loan amount is in thousands, income is in hundreds, and EMI is in dollars only. And we have discussed that for distance-based algorithms like KNN, features should be in the same scale. Else we'll get ambiguous results, and that's not what we want. In this case, we need to perform scaling with features, either scale up or down to bring all the features to the same scale. The two most common ways of doing feature scaling are min-max scaler and standard scaler. Let's first talk about min-max scaling. In this method, we first determine the minimum and maximum value in the column. Then for each value, we first subtract minimum value from it and then divide by the difference of maximum and minimum value of the feature, which is range. The min-max scaler scales down the value of the feature between 0 and 1. You can check that yourself if you want. Now, if you replace xi with a minimum value, the numerator will of course become 0, right? And when you replace it with a maximum value, both the numerator and denominator will cancel themselves and the ratio becomes 1. Here you can see in the second table, all values of these three features are now in the range of 0 to 1 after applying min-max scaling. Now let's look at the second method called standard scaling. In this method, we first determine the mean and standard deviation of the column. Then for each value, we first subtract the mean from the value and divide it by the standard deviation. Let's apply this on the same example. Here you can see that all values of these three features are now at a similar scale. Let's do one thing. Let's implement what we have learned so far in Python. In this video, we'll go through some feature scaling methods. So let's go ahead and import the libraries pandas and numpy, and we'll read the Big Mart sales dataset. Now we're going to focus on two features, item visibility and item MRP. As you can see, there's a huge difference between these values. So let's bring these features to the same scale. We are going to work with the min-max scaler here. It scales down the values between 0 and 1. You can see the formula here, but we don't have to use this. We'll rely on Python to do it for us, but it's always good to know and understand what's going on underneath the code. That's where the formula helps. So let's first import the min-max scaler from the sklearn.preprocessing library. Perfect. Now we'll create an instance called scaler, which we'll apply on the data, which stored the two variables, item visibility and MRP, as you can see here. And we're going to store this in a new data frame called scaled_data. Let's print out the first few rows. As you can see here, the variables now have the same range. Perfect. Now I'm going to use the .describe function to see the minimum value for both the variables. As you can see, it's 0, the maximum is 1. Perfect. Our min-max scalar worked exactly as we hoped it would. Let's try scaling these variables using the standard scaler. We'll pick the same two variables and we'll first import standard scaler from the sklearn.preprocessing library. Let me do that. Now we'll create an instance called scaler and fit it on the data. Again, we'll store it in a new data frame called scale data, and let me print out the results. Interesting. As you can see here, the mean is close to 0 and the standard deviation is 1. So these are the two methods, very popular methods, that we can use to scale our data. We have covered some pre-processing techniques for continuous variables so far. Let's move ahead to the feature pre-processing techniques for categorical variables. We'll start with a very popular one-hot encoding. It's often also called as dummy encoding. Remember this dataset? It's from the big math sales problem. We have 3 categorical variables highlighted in the red here. Note that most machine learning models cannot deal with categorical variables, especially in Python when we use scikit-learn. So we need to convert these categorical variables into numeric values. Let's pick the outlet size for now. Outlet size column, we can replace this outlet size column with 3 columns: outlet medium, outlet small, and outlet high. Now the first row has the outlet size medium. So we put 1 in the size medium column, as you can see here, and 0 in the other 2 columns. Similarly, we'll perform this step for the rest of the rows against respective outlet size. Here you can see for item identifier NCD 19, the outlet size is pretty high. So we have 1 in the size high column and 0 in the remaining 2 columns. The same method can be applied for the other categorical variables in our dataset, like the item type and the item fat content. But just hold on, there is a problem with this type of encoding. The item type does not have an order. As you can see, it just says names of items like dairy, soft drinks, meat, and we can't really say that there's an order to them. But the categories in outlet size and the fat content do have an order. For outlet size, small, medium, and high have an order in them, right? And by using one-hot encoding, we are actually losing this information. Such variables which have an order between them are called ordinal variables. In this case, instead of creating 3 different columns, we'll just replace the categories in the same column by numbers. As you can see in this example, we have numbers 1, 2, and 3 for small, medium, and high respectively. 1 for small, 2 for medium, and 3 for high. In this way, we are actually preserving the order information of the variable, as well along with encoding in numbers. So let's go and open our Jupyter notebook and try these techniques, one-hot encoding and label encoding. In this notebook, we'll implement the concepts of one-hot encoding and label encoding on the Big Mart sales dataset. Of course, you know what the first steps are. We'll import the pandas library and we'll read in the Big Mart sales dataset. Let me just bring up the first 5 rows. Here we go. We are very familiar with these variables by now. We've looked at them plenty of times before. So let's just check the shape. Perfect. We have 8500 plus rows and we're working with 12 columns of variables. Let's use the .dtypes function to bring up the data types. So the categorical variables here, we can see they have the data type as object. All of these are the categorical variables. And we need to convert these categorical variables into numbers before we train a machine learning model. So let's start by encoding a single variable, outlet type. We can determine the total number of categories in this variable using the .value_counts function. And as you can see in this output, we have 4 categories. We have supermarket type 1, grocery store, supermarket type 3, and supermarket type 2. Perfect. Now let's use one-hot encoding on this. Performing one-hot encoding is actually very simple in Python. All we have to do is use the pandas get_dummies function. So in this code block, I've applied this get underscore dummies function on the outlet underscore type variable. And as you can see in this output, we have replaced one column with 4 columns, which have binary values. Since the first row had the category supermarket type 1, we have 1 in that column, and all the other columns have 0. Similarly, for the second row, we have 1 under the column supermarket type 2 and 0 on the rest, and so on. But you might be wondering, if there are 10, 20 such variables, do we have to write this code line for every single one of them? Well, no. You can simply use get dummies on the whole dataset together. So let me go ahead and do that. Perfect. We can use the pd.get underscore dummies function and give the dataset name, like we've done here. It will automatically select the categorical variables and perform one-hot encoding. Now, we're faced with two problems since we've used one-hot encoding here. First is that all the categorical variables are converted into 0 and 1, which results in a loss of some important information. For example, the variable outlet size had categories high, medium and small, right? Which of course have an inherent order. But now look at what's happened when we've done this. We're missing out on some very important information because the order between these variables has now been destroyed. The second problem is that the number of features have drastically increased from just 12 to 1600 plus. Let's see the shape. You can clearly see we have 1605 variables. That is a humongous amount. And if we look closely, the variable item identifier has a number of unique values. It's essentially like an ID variable. And hence, there are more than 90% of the rows which have a 0 against them. Look at this. So this information is not really useful for the model. In this notebook, we will address the first problem and we'll look at the solution to the second problem in an upcoming video. So to maintain the order among the categories and variables, instead of using one-hot encoding, we'll go for label encoding. So let's go ahead and do that. We'll import the label encoder class from sklearn.preprocessing. Let me look at the value counts in the outlet size variable. Perfect. We have medium, small and high, and we have the value counts in front of them. Now we'll create an instance called LE and use the fit underscore transform function from the label encoder class. It will transform small as 2, medium as 1 and high as 0. Now the problem here is that label encoder considers the alphabetical order to assign values. That might not be what we're looking for every time. If we need an alternative solution to this, where we can decide the number we want to assign for each category manually, then we can use the .map function. Here's the example. Mention the variable name which you've done here, outlet size. Then we'll use the .map function and write the number against each category. Here I'm assigning 0 to small, 1 to medium and 2 to high. So let me just run that. Perfect. So that solves the first challenge that we've encountered in one-hot encoding. So far, we were dealing with categorical variables having less number of categories. Now imagine if your data set has a categorical column with 100 different categories. And it quite often does happen in the industry. So do you think one-hot encoding is a good idea? Not really. For example, here we have a sample data set with a column city. Imagine if this column has 500 unique cities. Performing one-hot encoding will create 500 different variables with 0 and 1 value. That's going to be an absolute nightmare to deal with. So what can we do? Well, here's the trick. We can combine sparse classes. But wait, what are sparse classes? Classes with relatively low frequency are known as sparse classes. Here's the value count for different cities. Cities having very low frequency, like Guwahati, Raipur and Indore, are less frequent in the dataset compared to other cities in the data. Since these cities have a very low frequency, we can combine these cities under a new category other to reduce the number of unique categories. And this will not explode the dimensionality of the dataset as well. So to reduce this number of categories, we can simply combine a few categories and hence reduce the overall number of classes for the variable based on the frequency count of variable. There can be different ways of combining as well if you have that domain knowledge. For example, in this case, I can combine similar cities together, and similarity can be geographic based or type of city based like tier 1, tier 2, tier 3. And also create a region variable which is one level up in the geographical hierarchy, but this is only doable if you have the geographical information. Let's go ahead and look at an example in Python. We'll continue working on the same notebook which we saw in the last video. So here we use the Big Mart sales dataset and we looked at what are the different categorical columns. We first used one-hot encoding on the whole dataset and discussed that we essentially have two problems that we're working with. Some variables might have an inherent order. That was the first problem. And the second was that the size has increased drastically. Remember, we started off with 12 variables, but after using one-hot encoding, we ended up with over 1600. To solve the first problem, we used the label encoding method. And now we can look at dealing with high cardinality or the high number of dimensions. To do this, we'll be reducing the number of categories. So let's first see which variable has the highest number of unique categories. We can do this using the .nUnique functions. Out of all the categorical variables, item identifier has the maximum number of unique values. Now this might be because each store has given a certain number or identifier to each individual item. Let's look at the value count for this variable. The maximum frequency is 10. And actually there are many values which occur just once or twice. So what we'll do is we're going to combine these low frequency classes. So we'll first store the frequency count of the variable in temp, and let me print out the first few rows. Okay, here we go. Now we'll create a new column in the data frame item identifier count, which will store the value count for each category. We'll do this with the help of the apply function. The apply function performs a given task for every row in the data frame. So here I've used the apply function on the item identifier column. For each category in the item identifier, it will return the frequency from the temp that we'd created here. So let me go ahead and run that. And finally, we want to combine the sparse classes. So for all the categories which have frequency less than 4, I've replaced the category with other. So let me run this for loop. It might take a couple of moments. So let's just wait for this to run. Alright, now let's look at the first 7 rows. Perfect. Now when we look at the value counts, we'll see that the least values we can see is 4. So the 1 and 2 values we saw earlier have now been combined. Alright, so we have so far covered numerous methods to perform feature preprocessing. In this video, we'll discuss the different methods for feature generation. Feature generation essentially means creating new features from existing data. Let's take an example to understand this. Suppose our problem statement is of stroke prediction and we're given this dataset. You can see that we have features like the person's age, we have gender, work type, hypertension, etc. And based on these features, we have to predict whether the person will have a stroke or not, which is essentially this column, the target variable. Now let's look at the relationship between the independent variables and the dependent variable. First, we have the age of the person. It's more likely that adults will have a stroke rather than kids. So we can create bins using this age column such that we classify adults in one bin and young people in the other. Now this can be done in various ways. The simplest method is the one we just discussed, where we set a cutoff at a value, say 35, and create 2 bins. The rows which have age greater than 35 will be marked 1 and others will be 0. So here we've created 2 bins. We can generate multiple bins in a similar manner. For example, set age 0 to 12 in one bin, 12 to 20 in another, and so on. In this case, we will have a new variable which will be categorical, or you can even say it will be ordinal in nature. Look at the example shown here. We have 4 categories: child, teenager, adult, and senior citizen. Since the variable here is age, we were easily able to decide the range values based on our experience. This cutoff value or threshold value can also be decided using a simple decision tree. We have built a tree using age as the only feature and stroke as my target variable. The decision tree decides the best split of age such that it is able to classify that person will have a stroke or not. Here we have threshold values as 49.5, 66.5 and 77.5. You can see here the first split has happened on 66.5. Then in the left branch of the decision tree, the split has happened on 49.5, and for the right branch it is 77.5. And we can now generate bins accordingly. Look at the bins again we have on this slide. Here are the cutoff values obtained using a decision tree model we saw in the previous slide. Let me bring up another example of binning. In this dataset, we have BMI values for each person, which, as you can see, are in decimals. Here we can round off the decimal values, for example 17.6 here and 17.7, which will both become 17. In a way, we are creating bins at a whole number level, right? Let's now move to the Python notebook and take a quick look at the implementation of binning in Python. Let's implement this concept. I'll go ahead and import the pandas library, and we'll be working with the same stroke prediction dataset that we saw in the video. So we have all sorts of variables here. We have the age, gender, hypertension, heart disease, if the person was ever married or not, work type, residence type, all sorts of things. And of course we have the final target variable stroke. So what I'll do here is I'll use the age variable to create bins. We'll first store the range for each category here in the bins variable. And this will be in the form of a list. These are basically the bin edges or the lower and upper values of the range. Then we'll store the names which we want to give these ranges. As you can see, I've given the following labels: child, teenager, young adult, middle-aged and senior citizen, and stored it in a group list, in a list called group. Finally, we've created a new variable, age_category, and we use the pd.cut function to bin the continuous values into categories. We give the variable age as input, and along with that we have specified the bin edges and the labels or the names for each group. So I'm going to go ahead and run this code block, and let's look at the first 5 rows. Perfect. As you can see here, our binning strategy has worked out perfectly. First row has age 3 and has been categorized as a child. The third 8 again a child. Age 58 falls into the middle-aged category, 70 into senior citizen, and 14 as a teenager. Perfect. Now the same can be done using the bin edges from a decision tree. We'll create a new list storing the new bin edges, as you can see in this code block, and the rest of the steps will be the same that we saw earlier. We create a list group that will store the labels. We are saying bin 1, bin 2, bin 3 and bin 4 here. And again we are creating a new variable age_category using the pd.cut function to bin the continuous values into categories by giving the variable age as input. Along with that we specify the bin edges and again the labels or the names for each group. I'll go ahead and implement this, and as you can see, our binning strategy yet again has come up trumps. The first row, which had age 3 for the person, is in bin 1, 58 is in bin 2, 8 is in bin 1, 17 bin 3, 14 again in bin 1. So I hope you got a sense of how binning works and how we can implement it in Python. Very interesting, wasn't it? All the examples that we have discussed so far were using a single variable. Let's look at some examples of how we can use more than one variable to generate new features, because that's essentially what you'll face in the industry or even when you're competing in a data science competition. Here, we have the loan prediction dataset. The target variable is the last column here, and we have to determine whether a loan should be given to the person based on the person's income, education, property area, etc. Now look at these two variables, the applicant income and the co-applicant income. Adding up these two values will give us the total earning of the family, which, as you can imagine, could very well be an important factor in deciding whether a loan should be granted or not. Since we have constructed a new feature which represents the interaction of these two features, this is called feature interaction. Similarly, we can construct other mathematical features like taking the ratio of loan amount and applicant income, or the ratio of loan amount and total income. The idea is that if a person or group with a high loan amount and low income might have higher chances of defaulting. Here again, having some domain knowledge will help you to think about these features. Moreover, we can use the difference of income and loan amount as well, and so on. It's not necessary that we use only two variables. You can go ahead and play around with multiple variables as well. So in this notebook, we are going to go ahead and implement what we've just learned. I'll import the pandas library first, read the dataset, and look at the first 5 rows of our loan dataset. And here we go. Now, after we load the dataset, we need to go through every feature and understand what each of these features mean, and try to identify the interaction of which feature would be useful for the model. So I've taken 2 examples for you in this notebook. First, since we're trying to predict if a person should be given a loan or not, apart from the person's own income, the income of the spouse could potentially be an important factor. In our dataset, we have 2 features, applicant income and the co-applicant income, which you can see here. We can add these two to get the total income. So I'm going to go ahead and do that and print out the first 5 rows. Here we go. You can add this up and it's perfectly visible in the total underscore income column. Awesome. We can create another feature, the loan income ratio. Here we are dividing the loan amount by the applicant income. So let me go ahead and do that. Perfect. And we have the loan income ratio in this column. And we've just created an entirely new feature. Don't you just love feature engineering? It's one of the most awesome aspects of a data scientist role. In the same manner that we've seen here, I would encourage you to go ahead, take up this data set and think of whatever features you can come up with. There are multiple ones. I can guarantee you can, if you just spend 10 minutes wondering which features you can create, you can come up with at least 20-25 new ones. In this video, we'll generate features based on available missing values. Let's say that we're doing data exploration in a data set and we find that the column smoking underscore status has a large number of missing values. Now our first intuition might be to delete this column, but missing values in the data might have a pattern, and in fact quite a lot of times tend to be useful. For instance, in this case, a missing value in that column might indicate that the person does smoke but is actually reluctant to say so. I mean, I'm sure a lot of us can relate to this. Hence, we can create a separate column that indicates whether this row has a missing value or not. There might be a chance that the missing value is not random at all, and there is some hidden information. Then this variable will capture that information. You can see here that I have created a column called smoking underscore status underscore NAN. It has 1 in the place where smoking status is missing. After this, you can impute the missing values like always. So let's move to the Jupyter Notebook and implement this method. We're going to use the stroke prediction dataset again. I'm going to go ahead and import the libraries and load the dataset. Here are the first 5 rows. We've already looked at this before. So what I'm going to do is I'm going to use the .isNull.sum functions to look at the number of missing values in each variable. Here we go. As you can see, the BMI and the smoking status variables have a ton of missing values, especially the smoking status here. So what I'll do is, in the next code line here, we are creating a new variable, smoking status NA, which will store 1 if there's a missing value and 0 if there are no missing values. I'll go ahead and implement it and look at the first 5 rows of these two variables. Perfect. So 1, remember, was when there was a missing value, and the smoking status confirms that yes, there is indeed a missing value here. 0 means there are no missing values, which again we can confirm against the smoking status variable. And that is how we can create new features using missing values. Pretty intuitive and straightforward, wasn't it? In this video, we'll cover another very commonly used feature generation method called frequency encoding for categorical variables. It's often used in data science competitions and has proved to work really well. It's even helped me out quite a lot of times. So let's understand what it is. Here we have a categorical variable work_type. Now we can determine the frequency of the categories in this variable and normalize the values. The idea essentially is that a category that has a higher frequency would of course have a higher number against it and hence will get more importance. For example, suppose there's an insurance company and they have various products, but they've not given information about their most selling product or so. In this case, frequency count will help us to give this implicit information to model using frequency encoding. Let me just do this in Python to give you a better idea of how frequency encoding works. Let's spend some time understanding how we can implement frequency encoding in Python. So I'm going to import the pandas library first, and let's go to the Big Mart sales data again. Here we have a variable item type, as you can see in this column, and I'm going to apply frequency encoding on this variable. Now when we look at the frequency of categories in this variable, you can clearly see that fruits and vegetables here have the highest frequency, followed by snack foods. So I'm going to go ahead and store the item type count in a variable called temp. Here we go, perfect. Now we'll create a new variable item type count using the .apply function. The apply function works like this, and we've seen this before. It will check the item type for every single row, and against the given category of item type, it'll return the frequency value from the temp variable we've just created. So I'm going to go ahead and run this. Perfect. So we've got the item type count against the item type. So dairy has 682 instances, meat has 425, and so on. Like we performed frequency encoding here, there's another commonly used method. It's called mean encoding. And this is often done using the target variable. Again, we have the item type variable and we're going to use the target variable sales. So let me just print out the first 5 rows. Here we go. So now against each category and item type, we can calculate the mean sales in the training data. Here we go. This shows us which variable or which item type has the highest sales. It's a brilliant way of understanding the different item types you have, what revenue they're bringing in. And not only have we just created a new feature, we can now analyze a lot of the things that we have in the Big Mart sales dataset using just this function. We've covered feature engineering with numerical and categorical variables so far. In this video, we'll be focusing on the date-time variable, and we learn how to generate more information from a date-time column. It's a very interesting concept. Can you think of a few examples where we'll find a time variable in our dataset? Here are a few off the top of my head. Suppose a particular hotel is collecting the data of their past bookings and they want to predict the number of room bookings for an upcoming month. A dataset for this problem statement would have features like the booking ID, booking date, the time of the booking, what kind of room was booked, the number of days and nights it was booked for, the number of people who stayed in the room, etc. I mean, there are a lot of variables that can factor in. So here we have two date time features, booking date and booking time. Another example is of predicting the price of flight for a particular airline. As you can imagine, the price would be higher during the time of vacation or during the weekend, while it should be lower during non-holiday seasons. What are the possible factors that can affect the price of a flight ticket? Here are a few I could come up with. The time of arrival and departure of the flight or the source and destination. Also, the date of travel is off-season or a holiday season also can be an important factor. We have three date time based features: date of travel, time of arrival and departure. Note that using the time of departure and time of arrival, you can determine the travel duration of the flight as well. Another example, and a very common one, could be of stock market analysis, where having the date, of course, is of utmost importance. Using the date, we can find if there is any pattern in the increase and decrease of the price. For instance, is the closing price more on Mondays and low on Fridays, or vice versa? Well, now that we understand that there are a number of problems where we can have the date time feature, let's see what valuable information we can extract from these date time variables. Using the date, we can determine which day of the week it is. Is it a Monday? Is it a Wednesday? And so on. We can also find out if the day is a weekday or a weekend. Any guess why this information would be important? Well, recall the example of the flight ticket price we discussed just a few moments ago. The ticket price would be considerably higher on weekends than on weekdays. So do you see where this fits in? We can also determine if the day is a national holiday or not, simply by looking at the date feature. This again would be useful when we work on problems like predicting the flight price or the number of bookings for a hotel. Using the date, we can also extract the month. For example, flight ticket price might be higher in December since it's close to Christmas. A summer vacations fall in June and the number of room bookings in a hotel during that month could see a significant rise. Similarly, we can determine the year from a given date. For instance, from a given data of the past 5 or say 10 years, the recent values would usually be given more importance. Now, considering the time feature, we can determine the hour from the time variable. How will this be useful? Well, the price of flight tickets at odd hours like 1 a.m. or so are usually significantly lower. And once you have the hour value, we can create more features like, is it morning, is it afternoon, evening, is it midnight? For instance, if you're trying to predict the sales of a product in a retail outlet, it would be more during the peak hours, right? In the same way, we can determine if it is the first or second half of the day. We can also calculate the difference between time, like calculating the flight duration. And the same goes with dates. Calculating the days of stay in a hotel, or calculating the age of a person using the date of birth and today's date, or the date he or she applied for a loan application or insurance. There can be a lot more features that you can create using the date variable. Apart from the features that we've discussed, you can see a lot of additional features here, such as the day of the week, the day of the year, what week of the year it is. I mean, there are a lot of variables. Here is a table that shows a list of features we can extract from a datetime column. We have taken this from the Pandas documentation and we've shared the link just after this video. So, apart from the features that we've already discussed, you can see a lot more features here, like the day of the year, the week of the year, which essentially represent the day number out of 365 and week number out of 52 total weeks in the year. Using the date, we can also find out its month start, month end, quarter start, quarter end, same for year, or is it a leap year or not. And so you can see the sheer amount of insight we can generate. Now let's look at an example. We have to predict the amount of NO2, nitrogen dioxide, in the air at a given day and time. How can we use the date and time variable here? I want you to pause the video and just think about it for a second before you proceed. NO2 primarily gets in the air from the burning of fuel. NO2 forms through emissions from cars, trucks, buses, power plants, and off-road equipment. So, intuitively, a higher amount we should expect to see in the morning between, say, 7 to 10 am, and in the evening between 5 to 8 pm, when people generally travel from office to work and vice versa. Also, during the afternoon, NO2 reacts with sunlight to form NO and O, but during the night this reaction does not take place. Let's do one thing. Let's jump into our Jupyter notebook and spend a few moments working with this dataset, which will give you a better idea of what we covered in this video. In this notebook, we'll go through the same example we saw in the slides. So let's go ahead and read the data. You can see we have dates in the first column and NO2 content in the second column. So here's a look at the different data types we have in these two variables. So date time, as you can see here, is being read as an object data type. Is that right? It's not. The first and most important step when dealing with the date time column is to convert the data type into date time. By default, as you can see here, it is taken as an object, and that can give us pretty random results. So what we'll do is we'll use the pandas pd.to_datetime function. We have to give the column name and the format as input. Format depends on the structure of your date column. Here we have date, month, year, followed by hour, minute, seconds. So this is how we can do it. So let me just print it out and then look at the data types again. Perfect. Here are a few examples of the different. So let me print the maximum and minimum values of our date time column. We get the minimum to be 10th March 2004, which is the first row of the data set. And you can verify from your end that the max value which you see here is actually the last value in the data set. To do this, use the dataframe.tail function. That's right, dataframe.tail. Now, let's see what are the features we can extract from this column. First, we can extract the hour and minute values by simply using the command column name .dt.r. So let's do that and look at the first 5 values. Here we go. These are the hours. So 18 would be 6 p.m., 7 p.m. and so on. We can also extract the minutes. So let's do that and print it out. It's 0 because it's 6:00 p.m. So you can just go through the entire data set to understand this in more detail. We can also extract which day it is, whether it's Monday, Wednesday or so on. We can do this using the column name .dt.day_of_week. So here I'll print it out. What do you think 2 and 3 here means? Well, this gives us the number where 0 is for Monday and 6 is for Sunday. If you want to get the name, then we can use weekday_name instead of day of week. So I'll print that out. Here we go. To get the month, we can use the dt.month function. So I'll print this out. Here we go. It's the third month of the year. So we can similarly determine the year using dt.year. That's something that you can do. Additionally, we can also find out if the given date is at the end of the month or the end of the year using the dt.is_month_end. So none of the dates, at least in the first 7 rows, are at the end of the month. You can always try other features yourself. In fact, I strongly recommend taking up this dataset or any other dataset that has a date time feature and experimenting around using what we've learned here or exploring other things that you can do with date time values. That's how you learn new things. Finally, what I'm going to do is I'm going to bring all of what we've learned so far together. So we'll create a new data frame called new_df using the pd.dataframe function. Here the first column is the year, which stores the year from the date. We have the month, day, hour, basically what we have just seen. And we also have an additional quarter here. We'll just put all of that together in a new data frame and print it out. Here we go. Here are all the new features that we've just created. How cool is that? Now I'll add all these features right back to our original data frame using the pd.concat function, basically concatenation. And here we have the new dataset. Isn't it amazing? We just had date underscore time and NO2 when we started. And now we have all sorts of very useful variables. Gotta love feature engineering. So far, we've discussed features we can directly create using pandas. Now, there are some additional features we might want to add to the data, like whether the given date is a weekday or a weekend. Since we were able to extract the day of the week, we can check if it's a weekend using this value. This is the code to do this. We've created a new column called is underscore weekday, and then we've run a for loop to check the value at each row. When the day of the week is 5 or 6, the value is 0. Otherwise, it's 1. 1 meaning weekday, 0 of course meaning weekend. So I'm going to go ahead and run this. Again, this is a computationally heavy for loop, so we'll just give it a couple of minutes to run. And then we'll look at the first 5 rows of our new data frame. And here we go. So day of the week 2 has is underscore weekday 1. 1, remember, is that it's a weekday. So clearly our for loop has worked out pretty well. These are the first 5 rows. Of course, you can look at the entire data set to verify all the values, but I can assure you our for loop has worked to perfection. We can also determine the difference between two dates. For example, I've taken up a new data set, which I'll just read, that has 2 columns, application date and the date of birth of the applicant. So application receipt date here and the applicant birth date. So I'll quickly print out the head of these 2 columns for easier use. Perfect. Using these, we can determine the age of the applicant. First, to do this, we need to convert these variables into the, that's right, date time format. So let me go ahead and run this. Alright. Now here's the difference of the 2 variables. It's 12,902 days. Divide this by 365 and you'll get the year. To do this for each row, I will again use the apply function. This code might look a bit complicated, but is actually very simple and efficient. For each row, .apply returns the difference of the 2 variables. And this value returned by the function is stored in a new variable, which we are calling applicant underscore age. So I'm going to go ahead and run this. Perfect. So this is how we can work with a date time variable. So many things we can do with a simple column. Again, as I mentioned earlier, go ahead, experiment with it. We have a time series dataset on Analytics Vidhya's data hack platform. Go ahead, use that dataset, apply what we have learned here, and you'll be amazed at the accuracy you get using these simple date time features. Is there any way we can automate this whole process of creating new features? Yes, we can. There's a library called Feature Tools, which is an open source library for performing automated feature engineering. Let's understand how it works. There are 3 important components of feature tools: entities, feature primitives, and deep feature synthesis. To thoroughly understand these, let's take up an example dataset, and it's one you've seen before. Can you recognize this? It's the Big Mart sales dataset. In this dataset, we have quite a few number of items like item weight, we have item type, we have the item MRP, outlet identifier, among other things. And of course, the last column here, the item outlet sales, that's a target variable. Now, in feature tools, this data set is called an entity. For now, we only have one data frame here, but there can be multiple. For instance, if we have a data set that holds only the variables that you can see in the red border here, like item identifier, outlet type, outlet size, etc. While we have another data set that contains the details about things like item weight, fat content type, and so on. In that scenario, we'll have 2 data sets, and each of these individual data sets would be called an entity. So an entity is basically a single table or data frame. All the information of the entity or entities is stored in an entity set. So in other words, we can say that an entity set is a collection of tables. Let's now talk about feature primitives. Remember we studied about feature transformations such as log or square before, as well as feature aggregations like additions and ratio previously. Well, these aggregations and transformations are called feature primitives. Here are a few examples of the various transformations and aggregations that we can implement using feature tools. You can go ahead and pause the video for a second and just go through this list if you want. So if I have the following two features, item weight and item MRP, from the Big Mart sales data set, we can take the sum or difference or multiplication and so on. But that's not the limit of what we can do. We can even add more variables. For example, item weight into item MRP plus item weight. You can think of the limitless things you can do using these options. This is the beauty of feature engineering. Now, this also is where the concept of deep feature synthesis comes into play. Deep feature synthesis stacks multiple transformation and aggregation operations. Although feature tools is able to create all these mathematical features automatically, but there's one thing you should keep in mind. It does not have domain knowledge, which, as we've seen previously, can play a critical role in building a better model. I would recommend using feature tools for generating new features, but you should also focus on domain understanding and apply that knowledge to create more domain specific features as well. Let's move to the notebook and implement this in Python. In this notebook, let's go ahead and understand how feature tools can be implemented in Python. Now, before we run this notebook, you'll need to install the feature tools library on your machine. Simply use this one following command and do that. So let's go ahead and import the feature tools library and pandas. Alright, we're going to be working with the Big Mart sales dataset. So I'll load that. And I'm going to store all the independent variables in the features variable and the target variable, which was sales, in a variable which we'll call y. Alright. Now first, we'll create an empty entity set using the function ft.entitySet. I've set the name of this entity set as Big Mart, as you can see here. You can of course set any name, whatever you see fit. So let me just run this code block. Here we go. Now we can add multiple entities to this entity set. Remember, each data frame is an entity. In our example, we only have one data frame, and hence, yes, we only have one entity. Now in this cell, we'll add an entity to the empty entity set we created earlier. How will we do that? By using the entity underscore from underscore data frame function. We'll name this data underscore 1, and as I said, you can use any name, and we'll add all the features, the independent variables, to this entity set. Also, we need to specify the parameter index, because in our data set we don't have a unique ID against each row. So I'm going to go ahead and run this. Perfect. Alright, now we've prepared the data according to feature tools. Time to create some new features. We will use ft.dfs function, which is the deep feature synthesis function. It returns two things: the newly created features, which we are storing in feature underscore matrix, and the feature definitions, which we'll store in feature underscore defs. To the function ft.dfs, we have to give the entity set, the target entity, which is data underscore 1 in our case. Target entity means which is our parent data frame on which we want to perform feature engineering. In case we have multiple data frames, we'll have to pick one of them as the target entity. Then we specify the function we need to perform on the features of the dataset using the trans underscore primitives parameter. I've specified two for now: add numeric and multiply numeric. Basically add all the numerical variables and multiply all the numeric variables. And we've set the depth to 1. We'll understand what the max underscore depth parameter does in just a moment. When I run this cell, we'll see that we have new features that we've added to our original entity. So let me go ahead and do that. Alright. Now, these are all the new variables starting here that we've now engineered out of our original entity. So let's see the complete list using the feature underscore defs code. Here we go. Here's the complete list. You can see a sum of two features. You can see the multiplication as well here of two features with all possible combinations. And when we look at the shape, we can see that now we have 23 variables and we started with 12. So we have created 11 new features. Now, if you look closely, each new feature is created by performing one operation, either addition or multiplication. Why do you think this is? This is because we set the max underscore depth to 1, so only one operation is being performed. Let's experiment and change the depth to 2, which we'll do that. So run these cells. Alright. So we get all sorts of new features again. Let's look at the complete list using the feature underscore defs code. As you can see here, the new features have a combination of 2 operations. And using this, we've created about 50 new features in a matter of seconds. Incredible! Feature Tools is a very powerful library for creating new features. But just a word of caution, not all the features will be useful for the model. So just keep that in mind when you're using it. Thank you.